So in the second video, in section 5.3, we're going to talk about independent events, and you're going to be able to determine if two events are actually independent, and then actually learn about the general multiplication rule for independent events. So events that are independent, they are two events, A and B, are independent if the occurrence of one event does not change the probability of the other event. So this one event has no change in the probability of the other event, or has no effect on the other event. So essentially what you have here, the probability of A happening, given that B has already happened, will just be the probability of A if they are independent. These two will be equal. And we're actually going to use this along with the reverse of that, probability of B, given that A has happened, the probability of B, to prove whether or not two events are actually independent. In this example here, our two-way table, we have male, female, and then dominant hand, left or right. And we have to determine whether or not male and right-handed are independent. So we're going to call event A male and then right-handed B. So what you have to prove is the probability of A, given that B already happened, is equal to the probability of A. If those two numbers are equal, then you can say that they're independent. If they are not equal, there's some effect that B has on A, and it's causing them to be unequal. Remember from our general multiplication rule, or conditional probability, that probability of A given B is the fraction probability of A and B divided by the probability of B. Okay. Now, probability of A and B. So that would be male and right. So male and right is 39 out of 100, or 0.39. Probability of B happening. B is right-handed. The right-handed, 90 out of 100, or 0.90. And the probability of A, that's male. Total here, 46 out of 100, 0.46. So when you simplify that, you're going to get approximately 0.43 not equal to 0.46. So what this tells you, because they're not equal, that B has some effect on A. So these two events are not independent, but they are dependent. If you go through the same math for B given A, that probability, to see if it's equal to the probability of B, the same exact math you use over here, you get 0.85 is not equal to 0.90, making them dependent events. Doesn't matter how close they are, they have to be exactly equal, otherwise they are dependent. Okay? All right, so multiplication rule for independent events. So if A and B are independent events, then the probability that A and B both occur is going to be equal to the probability of A multiplied by the probability of B. So that second factor is no longer like the general rule. It would have been probability of B given that A, but since these two events are independent, you know that A has no effect on B, so we no longer use that here. We just use the probability of B. So an example could be like on page 336, number 90. It says the Census Bureau says that our 10 most common names in the United States are, in order, Smith, Johnson, Williams, Brown, Jones, Miller, Davis, Garcia, Rodriguez, and Wilson. These names account for 9.6% of all U.S. residents. So the top 10, 9.6% of all U.S. residents. Out of curiosity, you took the authors, took a look at the authors from the textbooks for your current courses. There are 9 authors total. Would you be surprised if none of the names of these authors are among the 10 most common? So 9 authors. So what's the probability that none of the authors are in the top 10? So probability of none in top 10. So I have 9 authors to look through. That's 9 events. I have to do multiplication 9 times. Since it's 9.6% to be in the top 10, the complement of that would be 100% minus 9.6%. And you get 90.4%. Or as a decimal, which you will need to use as a part of the multiplication here, 0.904. So the probability of getting 1 not in the top 10 is 0.904. The probability of having all 9, you raise this to the 9th power, because you're going to have 1 author, 2nd author, 3rd author, 4th author, 5th author, and so on all the way up to 9. That's 9 events happening there. Multiplication rule says that they're all independent. You simply just multiply the probabilities. So this only shows 2 events, but this works for many events also. So 0.904 to the 9th power is 0.4032, or 40.32%. So the question asks you, would you be surprised if none of the names in the top 10 most common? The answer is no. That's not that small of a percent. It's almost half of 100%, or half of 1. Side note here, if you're looking at none, you should know that none, that phrase, and at least 1 are complements, meaning that those 2 events add up to 100%. So if you know this one, you could simply find the second one by doing 1 minus the probability of none. Or if you knew the probability of at least 1, you could do 1 minus the probability of this to find this. These 2 together will always add up to 1 because they are complements. Another example here, page 336, number 92. So 92 says, internet sites often vanish or move so that references to them can't be followed. In fact, 13% of internet sites referenced in major scientific journals are lost within 2 years after publication. If we randomly select 7 internet references from scientific journals, what is the probability that at least one of them doesn't work 2 years later? So, looking for the probability of at least 1 doesn't work. Now, from before, we just talked about, that's just 1 minus the probability of, and this is going to be somewhat confusing to say, none doesn't work. So none doesn't work really means they all work. So at least 1 and none are complements. But none doesn't work is just better said as all work. So what's the probability they all work? Well, if I have 7 of them and all working, the probability that they don't work is 13%, which means the probability that they do work is 87%, or 0.87. So this is do work, this is don't work. Complements again. So this is the number we're going to use, 0.87, and since we're choosing 7 of them, to the 7th power. So 1 minus 0.87 to the 7th power, when you do the math there, you get 1 minus 0.3773. And that finally becomes 0.6227, or 62.27%. That's the probability of getting all sites that work, or at least one that doesn't. Sorry, that's the probability of getting at least one that does not work, 62.27%, which is actually fairly high. So remember, at least 1, none, or complements. If you want to find 1, you could do 1 minus the other to find the probability. All right. One more thing to talk about in section 5.3 is kind of bringing together the idea of independent events and mutually exclusive events. They seem like special cases where there's no overlap or there's no effect on each other. You might mix up the 2 definitions. Let's just clarify real quick. mutually exclusive events or disjoint events cannot occur at the same time. Okay? Independent events can occur. This is simply saying that one event has no effect on the other one. Mutually exclusive, though, not the same thing as independent event. Because if you think about it, if two events are mutually exclusive, if one of those events happens, let's say A and B, let's say B happens, that means A can't happen. So therefore, A depends on B, and B actually depends on A too, because if A were to happen, then B couldn't happen. So these two things are not the same. So when you're talking about disjoint and independent, don't mix up the definitions. They mean two very different things. Mutually exclusive events are actually always dependent, not independent. They have their own formulas. You know what this looks like with a Venn diagram. Two circles that don't overlap. Those would be mutually exclusive or disjoint events.